friends, family, country people, lend me your ears to talk about research methods. Why? Because you're awesome. Also, this is important. This stuff's going to be coming up again and again. So let's learn it now. All right. We have talked about two different ways of going about research. You can observe naturalistic methods, case studies. You can start collecting quantitative observations like surveys, or you can move along to predicting things. You can use correlations to predict, but just remember that correlation does not mean causation. In order to do that, you have to go beyond observing, beyond predicting what you observe, and move on to controlling the thing that you predict that you observe. You need to be able to control for the things that are going to get in the way so that you can make a causal statement. You can say, this caused that to happen. And so this lecture is mostly going to be talking about what the thises and that's are in that part of research. And I hope you enjoy it. All right, we've already talked about observe and predict. And now we land here. We're talking about experiments. That's right. We made it. Experiments. We made it. We've arrived at the gold standard method to use with our super fantastic. I love using the phrase gold standard in case you couldn't tell. Experiments are the gold standard to test the gold standard of theories and the gold standard of ways of answering questions about the natural world, or the super fantastic way to answer any question about the natural world, including human behavior and experience. Experimentation. I don't know why I whispered the last part. Reverb. Fun stuff. Experimentation is the one method we have at our disposal to show causation. I don't still have verb on, do I? No. When experimentation hears, hey, correlation doesn't equal causation, it boldly steps forward confidently and says, hold my beer. I got this. Because being able to demonstrate causation is the very superpower of experimentation. In fact, it's the most powerful claim that can be demonstrated in the scientific method. In an experiment, an investigator manipulates the independent variable to determine its effect on the dependent variable. What? Oh, yes, it's true. In general, experimenters manipulate something. Let's say whether you play a violent or a non-violent video game, to see how that changes something else, like aggressive behavior as defined by length and intensity of white noise that you give to your opponent as pain. Okay. In this instance, the violence level of the video game is the independent variable. It's the thing that changes, right? And it changes because we manipulate it to change. We're literally giving one instance of violent video game and another instance of non-violent video game. This is the independent variable. And the aggressive behavior, since its change depends on whether or not the video game is violent, is called the dependent variable. All right. So the independent variable is the manipulation, and the dependent variable is what you measure afterwards. The independent variable is violent games or non-violent video games. The dependent variable is aggressive behavior as defined as intensity and duration of white noise in the ears of their opponents. Okay. You're going to hear me say that probably a zillion different ways. And also, hopefully you've read the chapter in the textbook. Also, hopefully you have seen the crash course. In order to test the effects on an independent variable or of an independent variable on a dependent variable, you need to break your sample up into groups. So let's talk about that. The experimental group, not surprisingly, is the one that gets the manipulation. In this infographic, the treatment group is also the experimental group. The experimental group receives the independent variable. In our example, it would be the group that gets the violent video game. And the control group doesn't. So you can either have the control group do nothing, but that might be people who don't do anything versus people who play video games, whether they're violent or not, might behave differently. So let's hold playing video games as a constant and just change whether one is violent or one is not. Okay. So now the control group has the non-violent video games. The experimental group has the violent video games. The dependent variable is measured in both groups, and that is performance on that aggressive white noise task. A key procedure for any experiment is to ensure that the participants that you've selected as your sample have an equal chance of being assigned to a group. So just like random sampling ensures a random selection from the population, once you have your sample and you break them up into groups, you want them to be randomly assigned to each group. And this is to safeguard against any group having a disproportionate amount of people with any particular trait. Another way to say that is by randomizing, you're ensuring that on average, you will not be getting a disproportionate number of traits in any one group because everyone in the sample has the same chance of getting into either group. Once you have your randomly assigned groups, you need to control for variance or any changes in the way the study is administered to each participant. This is done through standardization of how the test is administered, from the room they're tested in to whether or not they've eaten or drank anything before testing. While controlling for variables in a study, we're looking to reduce what are called confounding variables, or variables that could influence the outcome you're looking at, independent of your manipulation. Confounding variables are things a researcher knows or thinks may confound their results if they don't control for them. Unfortunately, the more control you exert in the lab, the less you can generalize into the real world. So you kind of need to strike a balance between controlling for confounds and your ability to maintain external validity. Even after controlling for confounding variables, experiments are prone to the effects of demand characteristics. These are cues that tell participants what the experimenter expects of them. And experimenter bias is another problem. To minimize demand characteristics and experimenters experimenters often try to conceal the purpose of the experiment. Further, an experimenter's expectations can influence the interpretation of behavior and the recording of data. So an experimenter has bias that they're not aware of. Sometimes subjects are picking up on cues and demand characteristics, and that's changing their behavior in ways that they're not expecting. So how do we build a firewall against this? Well, this is where blinding comes in. In addition to leaving participants blind to what is expected, to ensure objectivities, investigators can use blind observers who don't know what results are expected. So this table kind of gives you a breakdown of different kinds of single blinding and double blinding. So another way to put that is this plays out in either a single or double blind study design. In a single blind design, either the researcher or the participants, usually the participants, are unaware of expected results, right? Because if you know what's expected of you, you could lie and your data is therefore unreliable. Or even if you don't lie on purpose, you could, knowing what the goal is, you could perceive things in a way that would be different than if you were naive. And usually when we're testing as researchers, we want our participants to be naive. Okay, here's an example. Think of any taste test where participants are asked to choose one of two things that they have tasted. While the researcher knows what each sample is, the participant is blind to which is which, and they have to make the choice based merely on sensation and perceptions, but not expectations, right? So that's a single blind study. So as an experimenter, I'm giving you things to taste, and I'm asking you something like, which one of these two tastes creamier, right? I know which one has the higher cream content, but you don't. So you're blind to that. That is a single blind design. In a double blind design, I just want to make sure I didn't yes. In a double blind design, neither the observer nor the participant know the researcher's predictions. For instance, we may have a study where I know which group each participant is in, but I don't tell my technician who's administering the test, so they won't give away unconscious or nonverbal cues that the participant could pick up on to influence their behavior. So, for instance, I could make up all the solutions and put them in bottles that are labeled A, B, and C so that even my technician doesn't know what stimulus they're giving the person that they're collecting data from. In that instance, they are both blind to what's up, and therefore that is a double blind study. Let's assume you've done everything right. Based on observations, you have a hypothesis that you've crafted, listen to that, crafted with operational definitions for a theory that is parsimonious, falsifiable, and takes on the burden of proof. You've determined whether you're doing an observational or experimental study. You've collected quantitative data. You have an instrument that is relevant, reliable, and valid. You've selected your population, determined your sampling methods, and have randomly assigned your participants into the experimental group and the control group. You have controlled for confound variables, and you've dealt with experimenter bias and demand characteristics through blinding. Now you've collected all this stuff. What do you do with it? That is, how are we analyzing the data we've collected? And the answer is one word: statistics. All right. I know everybody here loves statistics. Whoa, turn that off. And I was being completely facetious. I know that nobody likes statistics except us nerds who do statistics. But we have to talk about it because A, it's important. B, it's important. It's just because it's important. Now, why is it important? Well, I know that there aren't many psychology majors this year, but just knowing the basics about statistics helps be a better critical thinker, right? You're less prone to folk psychology if you really understand numbers well. I'm not asking you to be a math nerd. We can talk about general concepts. Speaking of general concepts, what kind of statistics are there? We're going to talk about two different kinds of statistics. The first one is descriptive statistics. Descriptive stats is the first level of analysis. And it's named descriptive because these statistics literally describe your observed results in the form of mathematical summaries. When summarizing the results of an experiment, we care about the central score, that is, the middle or average. And there are three ways to represent an average or a measure of central tendency. One way of presenting the central score is a distribution, or a central score of a distribution is the mean. This is determined by adding all the scores and dividing by the number of scores. This is what's commonly meant when we say average. If I were to calculate the average age of the students in my class, or the average score of a continuous scale, I'd be using the mean. The mean is especially useful if the scores approximate the normal distribution, or bell curve, or normal curve. A symmetrical frequency of scores that clusters around a mean. So here in this infographic are 3 different examples of distributions. The one on the left is negatively skewed. The one in the middle is symmetrical. That's a normal distribution. And the one to the right is positively skewed. Another average is the median. The median is the middle score after all the scores have been arranged from highest to lowest. That's also called ranking. An appropriate use of a median is when you hear about differences in salaries, because most of the world's wealth is clustered to a slim minority of individuals. Wealth distribution doesn't fit well on a normal bell curve. Hence, the median is a more appropriate measure of central tendency. Median can also be used when collecting data where responses fall into categories instead of along a continuous line. For instance, if you're asking participants to rate something as either smelling like root beer or peppermint, and 20 participants choose one and 30 participants choose two, you can't report a mean of 1.6 because there is no category between 1 and 2. What is that, root mint or pepper beer? No, that's ridiculous. You have to use a different kind of statistics. So this kind of category data is called nominal data. And in addition to using the median, you can also use the mode on this kind of data. The mode is the score that occurs most frequently. All right, so we have the mode, the median, and the mean. Again, if you take a look at the 3 different distributions, the negative, negatively skewed, symmetrical, and positively skewed, you can see that depending on what kind of data you're looking at, there are more or less appropriate measures of central tendency to use. If you used the mean when you should use the median, for instance, look at that negatively skewed data. Well, those data points are pretty far apart from each other. So if you're trying to talk about a mean salary versus the median salary, you might be talking about 2 very different numbers, and that could be used against people that don't understand what a median is versus a mean versus a mode. All right. Once we've reported the descriptive statistics, and here's just another iteration of the normal distribution. Once we've reported the descriptive stats of the data we've collected, we may want to make inferences about any differences that we see between our groups and whether they can be generalized to a larger population. Enter inferential statistics. Inferential stats determine the probability that purely chance variation would achieve a difference as large as the one that is observed. In other words, is it due to chance? Is it due to chance? That is, it determines how confident you can be in your results by comparing your observed results to what you would expect to happen by random chance. So if we're using inferential stats to calculate the probability that a given research result would have arisen by chance, we'd want that probability to be low, right? So walk through this with me. If you have a result that you want to impress someone with, and they ask, yeah, but what's the probability that this is due to chance? You want to say, the probability of this being due to chance is low, quite low. That probability of this being due to chance, that is low, son. Low probability. I don't know why I got so indignant at the end there. Flashbacks from poster presentations, but I think you get the point. The result of inferential stats is summarized by the p value as in probability. The smaller the p value, the lower the probability and the more impressive the results, right? The lower the probability of what? Of your results being due to chance. The usual agreement is that if p is less than 0.05, researchers consider the results to be statistically significant, which chance alone would be unlikely to produce. The p-value of 0.05 represents either a 5% probability that the results are due to chance or 95% confidence in your results. Either way you want to look at it. Other more stringent criteria for statistical significance include a p-value of 0.01, representing a 1% probability the results are due to chance. Also, there is a p-value of 0.001, representing a 0.1 probability that results are due to chance, or another way to look at it is a 99.9% confidence in your results. And those are impressive indeed. And of course, if your p is even lower than that, the better. There's three factors that influence statistical significance. There is the size of the difference between the groups. There's the number of research participants. And then there's the amount of variation among individuals. The reason why I bring that up is because there are critiques and objections to the procedure yielding p-values. One objection is that it falsely implies an all or nothing judgment. Either something is significant or it's not, right? More realistically, results range along a continuum from convincing to unimpressive. A second objection is that we should care about the size of the effect, not just whether or not it occurred. Given a large enough sample, it would be possible to get a low p-value even for a tiny effect with no practical importance. And that's just that's an effect of numbers. The larger your sample size, the lower your error bars, the more different things are going to look, even if those aren't differences that make a difference. To address these critiques, some researchers are suggesting that the raw p-value should be reported instead of setting these bizarro criteria. They're not bizarre, they're just arbitrary, and that's what makes it bizarre. So 0.5, 0.1, 0.001. This lets the reader determine significance for themselves because it isn't a predetermined alpha level or p-value. Instead, it's just the raw p-value being reported. All right, we did it. We've covered basic research methods used in psychology. And even though I placed value on certain methods other than others, psychology is not limited to just one technique or research method, or even one statistical analysis. Experiments are good for causality, but artificial because of all the things that need to be controlled for. Correlational studies allow for realistic environments, but they can't infer causality. Naturalistic observation is the most realistic, but least powerful for inferring causality. You can use a combination of the three in any method, in any design, to get a more robust result. Okay, we're going to wrap this up with replicability. Now, as I had mentioned before, the ability to come up with a hypothesis that either goes towards a theory or supports a pre-existing theory. Your ability to get it through the process of an experiment, that's not the end. When you're done with an experiment and you put it out, into the intellectual commons for other laboratories and researchers to replicate, you are now putting yourself up for scrutiny for your theory to be falsified. But if a bunch of different labs repeat your study and get the same-ish results over time, all of those different studies can go into what's called a meta-analysis. But before we get to a meta-analysis, let's just go over the idea that if you have an idea that you tested and other laboratories also test it and get similar to the same results as you, that means that what you're looking at is pretty powerful. But how do we determine how powerful? What is the effect size of this? Well, once a study's been replicated, all those studies can go into a fancy schmancy analysis that is called a meta-analysis. Meta-analysis just takes the results of many experiments, got to turn it off at the end, and determines an overall effect of the phenomenon being tested. Here's the same slide I showed at the beginning, again, reiterating the levels, the hierarchy of evidence. Anecdotal stories are evidence, but weak as compared to randomized controlled trials. And randomized controlled trials are even underneath the hierarchy of meta-analysis. Meta-analysis. All right. Let's wrap it up by talking about the ethical concerns. As I mentioned at the beginning of the lecture, psychology differs from other sciences in that we test animals, including human animals, which raises ethical concerns above and beyond methodological concerns. Once you've developed your research study, but before you begin recruiting, you need the approval of what's called an institutional review board, or an IRB, whose responsibility is to protect research participants. For human participants, the IRB judges whether the proposed studies include procedures for informed consent and whether they safeguard each participant's confidentiality. An IRB also tries to prevent risky procedures, or it informs the participant of the level of risk. A committee would also ban procedures that they consider seriously embarrassing or degrading. Before conducting any study on people, researchers ask for their informed consent, a statement that they have been told what to expect and that they agree to continue. When researchers ask for volunteers, they describe what will happen. Participants are told they have the right to quit if they find the procedure too disagreeable. Special problems could arise in research with children, people with mental retardation, or what was called mental retardation, what's now called intellectual disability, or others who might not understand instructions well enough to provide informed consent. In such cases, researchers either consult the person's guardian or nearest relative to receive assent instead of consent. So these two pictures right here. When we talk about social psychology, we're going to be talking about the Stanford prison experiment. And that's the picture to the left. And we're going to be talking about Stanley Milgram and his obedience studies. And that is the picture to the right. And these studies would not be able to be done today because they didn't have informed consent. They were deceptive in ways that are unethical. But almost because of them, institutional review boards quickly took up the helm to ensure the safety of participants in research. Now, there's also non-human participants, you have to remember, and animal research has long been essential for preliminary testing of most new drugs, surgical procedures, and methods of relieving pain, and most psychologists support some kind of animal research, most drawing a line somewhere between separating acceptable from unacceptable research. Professional organizations such as the Society for Neuroscience and the American Psychological Association publish guidelines for the proper use of animals in research. Further, colleges and other research institutes maintain laboratory animal care committees to ensure that laboratory animals are treated humanely and that their pain and discomfort are kept to a minimum, and that experimenters consider alternatives before imposing potentially painful procedures. Wow, there's a lot of alliteration on that last one. Okay, we did it. It took a while, but we did it. We talked about the scientific method, the super fantastic way to answer any question about the natural world, including human behavior and experience, by talking about hypotheses and theories, populations and samples, research methods, statistics, replicability, and ethical concerns. Thank you for joining me on this wonderful ride through research methods of psychology. Have a wonderful day.